Now let's look at different forms of energy. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical and nuclear energy. And there are some constitutes of the total energy, capital E, of a system. The total energy of a system on a unit mass basis is denoted by simple E and is expressed as simple E equals capital E divided by M in kilojoules per kilogram. Thermodynamics provides no information about the absolute value of the total energy. It deals only with the change of the total energy, which is what matters in engineering problems. Thus, the total energy of a system can be assigned a value of 0 or capital E is equal to 0 at some convenient reference point. The change in total energy of a system is independent of the reference point selected. The decrease in the potential energy of a falling rock, for example, depends on only the elevation difference and not the reference level selected. In thermodynamic analysis, it is often helpful to consider the various forms of energy that make up the total energy of a system in two groups, macroscopic and microscopic. Macroscopic forms of energy are those a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential energies. The microscopic forms of energy are those related to the molecular structure of a system and the degree of the molecular activity, and they are independent of outside reference frames. The sum of all microscopic forms of energy is called the internal energy of a system and is denoted by a capital U. You will notice that at least 6 different forms of energy are encountered in bringing power from a nuclear plant. These include nuclear, thermal, mechanical, kinetic, magnetic and electrical forms of energy. Nuclear energy would be for releasing energy from fission or fusion. Thermal for steam generation. Kinetic and mechanical for turning the turbine. Magnetic for generation of electricity in the generator. And finally, electric energy that is transmitted from the power plant to your home. The energy that a system possesses as a result of its motion relative to some reference frame is called kinetic energy. When all parts of a system move with the same velocity, the kinetic energy is expressed as simple m capital V squared divided by 2. Or on a unit mass basis, it is denoted as simple Ke, which is equal to capital V squared divided by 2 in kilojoules per kilogram. The energy that a system possesses as a result of its elevation in a gravitational field is called as potential energy, given by capital PE, and is expressed as capital PE equates simple m, g and simple z. And on a unit mass basis, it's given as simple PE, which is going to be equal to simple g times simple z, given in kilojoules per kilogram. In these instances, the simple m is mass, whereas simple g is the gravitational acceleration and simple z is the elevation of the center of gravity of a system relative to some arbitrary selected reference level. The magnetic, electric and surface tension effects are significant in some specialized cases only and are usually ignored, and in the absence of such effects, the total energy of a system consists of the kinetic, potential and internal energies and are expressed as capital E would be equal to capital U plus capital Ke plus capital Pe, which would also be equal to capital U, which is internal energy, plus the kinetic energy portion, which is going to be mv squared divided by 2, and the potential energy portion, which equates to mgz. And on a per unit mass basis, you would notice that the simple E, total energy per unit mass, is going to be equal to simple U plus simple Ke, kinetic energy, plus simple Pe would be equal to simple U plus V squared divided by 2 plus Gz. And the units would be kilojoules per kilogram. And you will notice that simple E, which is the total energy per unit mass, is going to be equal to capital E divided by M, denoted by kilojoules per kilogram units. Most closed systems remain stationary during a process and thus experience no change in their kinetic and potential energies. Closed systems whose velocity and elevation of the center of gravity remain constant during a process are frequently referred to as stationary systems, the change in the total energy delta capital E of a stationary system is identical to the change in its internal energy, which is delta capital U. And in this text, a closed system is assumed to be stationary unless stated otherwise. Control volumes typically involve fluid flow for long periods of time, and it is convenient to express the energy flow associated with a fluid stream in the rate form. This is done by incorporating the mass flow rate, simple m dot, which is the amount of mass flowing through a cross-section per unit time. It is related to the volume flow rate, capital V dot, which is the volume of a fluid flowing through a cross-section per unit time, and mass flow rate, m, simple m dot, is going to be equal to rho, capital V dot, is going to be equal to rho AC, V, capital V average, where AC is the cross-sectional area and V average is the average velocity. Here, the mass flow rate, simple m dot, the units would be kilograms per second, which is of course is analogous to simple m is equal to rho, capital V dot, where rho is the fluid density and capital A sub c is the cross-sectional area of flow, and as I said earlier, capital V average is the average flow velocity normal to the cross-sectional area capital A sub c. And the dot over a symbol is used to indicate time rate throughout this discourse. The energy flow rate associated with a fluid flowing at a rate of simple m dot by capital E dot is equal to simple m dot times simple E in kilojoules per second or kilowatts, which is analogous to capital E is equal to simple m times simple E, where simple m is the mass and simple E is the total energy per unit mass. Internal energy is defined earlier as the sum of all microscopic forms of energy of a system. It is related to the molecular structure and the degree of molecular activity and can be viewed as the sum of the kinetic and potential energies of the molecules. To have a better understanding of internal energy, let us examine a system at a molecular level. The molecules of a gas move through space with some velocity and thus possess some kinetic energy. This is known as the translational energy. The atoms of a polyatomic molecule rotate about an axis, and the energy associated with this rotation is the rotational kinetic energy. The atoms of a polyatomic molecule may also vibrate about their common center of mass, and the energy associated with this back and forth motion is the vibrational kinetic energy. For gases, the kinetic energy is mostly due to translational and rotational motions, with vibrational motion becoming significant at higher temperatures. The electrons in an atom rotate about the nucleus and thus possesses rotational kinetic energy. Electrons at other orbits have larger kinetic energies. Electrons also spin about their axis, and the energy associated with this motion is the spin energy. Other particles in the nucleus of an atom also possess spin energy. The portion of the internal energy of a system associated with the kinetic energies of the molecule is called as the sensible energy. The average velocity and the degree of activity of the molecules are proportional to the temperature of the gas. Therefore, at higher temperatures, molecules possess higher kinetic energies, and as a result, the system has a higher internal energy. The internal energy is also associated with various binding forces between the molecules of a substance, between the atoms with a molecule, and between the particles within an atom and its nucleus. The forces that bind the molecules to each other are, as one would expect, strongest in the solids and weakest when it comes to gases. If sufficient energy is added to the molecules of a solid or a liquid, the molecules overcome these molecular forces and break away, turning the substance into a gas. This is a phase change process. Because of this added energy, a system in the gas phase is at a higher internal energy level than its solid or liquid phase counterparts. The internal energy associated with the phase of a system is called as the latent energy. The phase change process can occur without a change in the chemical composition of a system. Most practical problems fall into this category, and does not need to pay any attention to the forces binding the atoms in a molecule to each other. An atom consists of neutrons and positively charged protons bound together by a very strong nuclear force in the nucleus and negatively charged electrons orbiting around it. The internal energy associated with the atomic bonds in a molecule is called as chemical energy. During a chemical reaction, such as a combustion process, some chemical bonds are destroyed while others are formed, and as a result, the internal energy changes. The nuclear forces are much larger than the forces that bind the electrons to the nucleus. The tremendous amount of energy associated with the strong bonds within the nucleus of the atom itself is called as nuclear energy. Atoms may also possess electric and magnetic dipole moment energies when subjected to external electric and magnetic fields due to the twisting and the magnetic dipoles produced by small electric currents associated with the orbiting electrons. The forms of energy already discussed, which constitute the total energy of a system, can be contained or stored in a system and thus can be viewed as the static forms of energy. The forms of energy not stored in a system can be viewed as dynamic forms of energy or as energy interactions. The dynamic forms of energy are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a closed system are heat transfer and work. The energy interaction is heat transfer if its driving force is a temperature difference. Otherwise, it is work. A control volume can also exchange energy through a mass transfer, since any time mass is transferred into or out of a system, the energy content of the mass is also transferred with it. In daily life, we frequently refer to the sensible and latent forms of internal energy as heat, and we will talk about heat content of bodies later in the chapter. In thermodynamics, however, we usually refer to those forms of energy as thermal energy to prevent any confusion with heat transfer. Now let's learn about mechanical energy. Mechanical energy can be defined as the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. Kinetic and potential energies are the familiar forms of mechanical energy. Thermal energy is not mechanical energy, since it cannot be converted to work directly and completely. A pump transfers mechanical energy to a fluid by raising its pressure, and a turbine extracts mechanical energy from a fluid by dropping its pressure. Therefore, the pressure of a flowing fluid is also associated with its mechanical energy. In fact, the pressure unit Pascal, PA, is equivalent to newtons per meter squared, or Newton times meter divided by meter cubed, which would be equal to joules per meter cubed, which is energy per unit volume, and the product capital P times simple V, or it is equivalent capital P divided by rho, has the unit of joules per kilogram, which is energy per unit mass. Note that pressure itself is not a form of energy, but a pressure force acting on a fluid through a distance called flow work in the amount of P divided by rho per unit mass. Flow work is expressed in terms of fluid properties, and it is convenient to view it as a part of the energy of a flowing fluid, and we call it flow energy. Therefore, the mechanical energy of a flowing fluid can be expressed on a unit mass basis, as you can see in this equation, where E sub mech is unit mass basis, and it is given in lowercase, would be equal to P divided by rho, which is the flow work or flow energy, and V squared divided by 2 plus Gz. So mechanical energy of a flowing fluid per unit mass again is going to be equal to flow energy, which can be depicted as capital P times simple V, or capital P divided by rho, plus the kinetic energy portion as well as the potential energy portion. The energy could also be expressed in the rate form as capital E dot mechanical, or mechanical energy in the rate form per unit time basis, that is given by the dot, is going to be equal to m dot simple E mech would also be equal to m dot times P divided by rho plus V squared divided by 2 plus Gz. Here m dot is mass flow rate of the fluid. Then the mechanical energy change of a fluid during incompressible, where rho is going to be a constant, flow becomes delta E mech is going to be equal to P2 minus P1 divided by rho plus V2 squared minus V1 squared divided by 2 plus g gravitational acceleration times z2 minus z1. Here note that the subscripts 1 and 2 are for states 1 and 2 respectively. And the rate of mechanical energy change of a fluid during incompressible flow, which is denoted by delta capital E dot mechanical, is going to be equal to simple m dot times change in E mech, simple E mech would be equal to simple m dot times the pressure difference divided by rho plus the velocity difference squared divided by 2 plus gravitational acceleration times the difference in height, which is z2 minus z1, and the answer comes in kilowatts. So let's see how we can estimate mechanical energy. The mechanical energy of a fluid does not change during flow if its pressure, density, velocity, and elevation remain constant. In the absence of any reversible losses, the mechanical energy change represents the mechanical work supplied by the fluid or extracted from the fluid. So if you consider the state A, consider points 1 and 4 for states 1 and 2 in the given equation. Is that P1 is equal to P4, or the pressure of those 2 points are going to be equal since they are exposed to atmosphere. And the velocity V1 is going to be equal to velocity V4 since the fluid is stationary between the 2 points. And the work done would be equal to m dot GH. If we consider the situation B, where points 2 and 3 are considered for states 1 and 2 in the equation, we will notice that the velocity V2 is going to be equal to velocity V3 because there is no change in fluid velocity. And you will also notice that Z2 is going to be equal to Z3, the height or the elevations, because there is no change in elevation. And the work done is going to be m dot dp divided by rho.